So I was talking about what happens during the freeze drying process, right? So the water molecules will come together, nucleate together among themselves, and then they will crystallize. So they will form a water crystallization network. So the white parts are water crystallization network in your drug, okay? And then the API and excipients are pushed away from water, so they are existing kind of separate entity from water. Okay, so then the main question is, in what condition are those API and excipients existing in this space called interstitial space, this space, okay? So they may exist as eutectic mixture condition or glassy condition. So these are the possible conditions. So ice forms, and then what happens to your drug molecule and excipients, right? So eutectic formation is one possibility, or metastable glass condition is another possibility, or stable condition, glass condition is another possibility, or lyotropic liquid crystal conditions. Okay, so these are all possible states for your drug molecule, how they exist in the interstitial space. Okay, so eutectic is a kind of perfectly ordered crystalline state, so that's probably the desirable form. So very orderly crystal form, if your drug molecule exists, that's probably the best form. Okay, and then stable glass or metastable, unstable glass is another possibility. So stable glass or unstable glass, these are two other possibilities. And then lyotropic, kind of sticky, kind of liquid crystal, kind of, liquid and crystal mixed up together, mixture of liquid and ice together. That's kind of the possibility, but that's kind of an undesirable condition. Okay, so we'll talk about those a little bit more. So eutectic is a pure compound. If you have eutectic condition, eutectic crystal condition, that's a pure compound that can be melted. Very characteristic temperature. Eutectic is a solid form of two or more crystalline material that are in such close contact, so they melt like one pure compound. So that's the most desirable condition where your drug should be during your freeze drying. It's going to give a nice cake appearance. In the glassy condition, glassy or amorphous phase material is also a solid forms with no order to the molecule. So it's organized very precise crystal structure called the crystalline lattice. The molecule is in so crystal is a better condition than, of course, the amorphous phase. It's a more complete disorder form. Okay, so between the glass crystal form and then metastable crystal form, of course, glass crystal form is a better form. Okay, so again, so eutectic is the best. Then next form is maybe glass crystal form, and then next form is maybe metastable glass form, and the worst form will be amorphous form. Okay. So yes, that's what happens. So while freeze-dried products can have either eutectic or glass in their interstitial space, it is not common for product to contain both phase in the same product. So there are kind of various possibilities that exist. That's what it means. Okay. So eutectic type, glassy type, they behave really differently. So scientists should figure out, what condition your drug will exist during the freeze drying condition, and try to come up with the best freeze drying process for your drug. Okay, the best freeze drying, temperature condition and then pressure condition. Okay, so it is also extremely important to determine the temperature where the eutectic phase and glass phase melts. Okay, so you understand the melting temperature, and then your freezing temperature during your freeze drying should be lower than the eutectic melt and glassy melt points. So to define eutectic temperature, or glass transition temperature, and collapse temperature, three different temperature points are really important. Okay, so your freezing point should be much lower than these. So main steps in freeze drying process. Okay, So number one step, okay, after placing your drug inside of a freeze dryer, the first treatment will be the product freezing. Okay, you have to freeze, of course, the liquid water should be crystallized, right? So 5% solute and 95% solvent. Normally, that's how your drug, injectable drug, exists. A lot of water. Okay? So you're gonna cool the temperature to a temperature below the eutectic point, the glass transition temperature. So everything will be solid, frozen. Okay, frozen solid. Okay? So it's about -40 or -50 degrees in Celsius. Okay, and then once product is frozen, as we said, your drug molecule could be in crystalline state conformation or status, or amorphous glass status. If it's crystalline structure, then eutectic is very good, right? So understand. An amorphous product have a corresponding glass transition temperature, okay, or collapse temperature. So you need to understand those. So eutectic is often used to describe the freezing melting points of any products. Okay, so again, these temperature points are very important in developing freezing drying cycle of the product, and are characterized through instruments called DSC. DS stands for differential scanning calorimeter and freeze drying microscopy. Okay, there are two important pieces of instruments that you need to use when you develop the freezing drying process. Okay, DSC and the freeze drying microscope. Okay. So once primary freezing is done, then there may be a secondary freezing step. We call that secondary freezing step as thermal treatment step or annealing step. Okay, what that means is, and after first freezing step, your drug may not be in full glass condition or eutectic condition. Okay, some parts may be frozen, some parts may not be frozen. So it's like metastable glass foam or amorphous foam, right? So then you have to maybe freeze it better, crystallize your drug molecule better. So how do you do that? You do that by treating your drug with a thermal treatment process. Normally it's called annealing process. And what is that process? It's kind of a quick thawing and freezing, repetitive process of thawing and freezing. Okay, so few hours of melting and freezing over and over, then you get a better crystallization. That's what annealing process is. Okay, so when you do that, then you can get a better crystallization of your drug through a process called Oswald ripening. That's a small ice crystals in the ice channel that melts, and then it's frozen again. When it's frozen again, it can form a large cluster of crystal. So by doing so, you can get a better crystallization of your drug. So that's what annealing is for, and that annealing is developing a larger crystal through a process called Oswald ripening. Okay, so that's what happens during the thermal treatment or annealing process. So during annealing, the metastable system in the interstitial space will liquefy because you heat it up quickly, and as it exceeds its glass transition temperature and then quickly crystallize to form the more stable crystalline eutectic phase, and you heat it up a little bit and then you freeze it again, and when you freeze again, then you can form a larger crystal. Okay, so that's what you're doing. Okay, so technically annealing is considered to be part of the freezing process. Okay, because you're not pulling any vacuum yet. Okay, so combining both primary freezing and annealing, you're still trying to freeze your drug. Okay, once your drug is frozen, it's in maybe eutectic or crystalline glass condition, then now you can start pulling vacuum to remove water, right? Sublimation can take place. So vacuum pulling is the third step. So system evacuation. So what's evacuated? It's the water evacuated as vapor form, right? So that's the third step. Okay, once freezing phase and annealing phase is done, complete, the vacuum is started and primary drying state. So the vacuum is pulled under the frozen state. That's what it means. So the core temperature is not changed, okay, but vacuum is slowly pulling. So slow vacuum pulling will start. Okay, so when you start this, you need to understand vapor pressure. What it means is you should be able to establish a gradient of pressure, okay, where your drug vial should be the highest pressure, and then it's going to flow towards the condenser where vapor will be crystallized again. So from the higher pressure, your vapor will travel from the inside of the vial. It's going to go to outside in the chamber, freeze-dried chamber, and then it's going to go down to the condenser where the pressure will be the least. Okay, so there should be a flow of, I guess, vapor established through the difference in the pressure. Okay, so the vapor pressure is the highest pressure point inside of the vial. Okay. So by creating that gradient, escaping tendency is established. That means the water vapor will escape from the vial, and it's going to travel down to the condenser inside of a freeze dryer. Okay, so that's what it means. So they increase the headspace pressure. That's the pressure inside of your vial. Okay, so in this pressure achievement, pressure condition, so temperature has an effect, okay, on this pressure, but the vapor pressure. So what it means is if you heat up the temperature, the vapor pressure inside a vial will increase dramatically. Actually, there's a kind of exponential relationship. Okay, so temperature and vapor pressure shares kind of exponential relationship. Okay, so so we talked about vapor pressure. Okay. Okay, so that's where your drug is vaporized through sublimation. Okay, so that's the vapor pressure is increased in the headspace of the vial. Okay, so when you achieve that, the temperature has a greater effect. So that's why you want to maybe change the temperature slowly from the totally frozen state. You're going to maybe crank up the temperature. Okay, once the vacuum pressure is established. Okay, so like liquid, ice in the ice channel has a vapor pressure that is affected by temperature. So that is the basis of primary drying in the freeze drying conditions, the first drying process. So that drying process is established through the temperature slowly rising, okay, from the primary freezing condition. Okay, so the warmer the frozen sample, the higher the vapor pressure of the ice. Okay, so when you have a higher temperature during the drying, then you can establish higher vapor pressure. That's what it means. Okay, the faster the sublimation rate, meaning you can vaporize more ice crystal. That's what it means, because the vapor pressure is high, and the faster will the vaporize and go to the condenser, resulting in shorter primary drying time. Okay, so understand how temperature would affect the vaporization process. So the driving force in free drying is not temperature but pressure. But the pressure is established by the temperature, so there is a relationship, right? And the pressure in the product must be higher, created by the water vapor being generated, than the pressure around the condenser, meaning there should be a gradient of the pressure. So inside a vial is higher than the outside of vial, especially condenser, where the vapor will end up and then they'll become crystallized again. Okay. The vapor pressure of the ice as a function of temperature is well understood. Okay, it's the graph we just looked at, right? So by controlling the vacuum to keep the chamber pressure lower than the vapor pressure of ice, ensures that water vapor will travel consistently from the product vial to the condenser. So that's what's achieved during the drying step. So vapor pressure over ice temperature value. So ice temperature versus vapor